Just one person on life size? Whatever. All right. So for a second. Oh yeah, in Vancouver, their power might be down, right? Who knows?
Sure.
It's raining hard there. All right. So
I just had a meeting with them.
why? Oh, hold on, my video here. There we go. Video. Yay! Everything's going good. There's audio, video, and plugged in. You guys can hear me. We'll do a screen share in just a moment. But first, so and we're going to switch this over to this. Yeah, it's pretty good. A little short, but that's all right. Yeah, no specular. Oh, look, the lights are back. All right, it's been almost a month. Well, it's been 3 weeks, 4 weeks, 3 weeks since we've had a Chalk Talk, and we're going to do it. This one, the last time we were Chalk Talking, we were talking about autoencoders, and this time well, as with all Chalk Talks, it's going to be as sloppy as all get out. But we have a plan. We're going to start off with autoencoders, which basically takes like a number, moves it through a neural network with a whole bunch of nodes. And we'll put some more neural networks here. An output, which turns into, hopefully, number 7. And all these things are connected, right? So we have all these connected where we're back to machine learning again. The promise of this, we've done this with just autoencoders. Autoencoders will allow us to create new images that we've never seen before in the same class of images that we've trained this to. Let me keep drawing here, just to make sure that everybody's up to speed. But before we get that, and we're actually going to do that. I'm going to do this when I turn on screen sharing this and show you what a basic autoencoder does. We're going to stay on autoencoder land for the next probably, well, certainly today, because today we're going to talk about how to actually implement this using Theano and Lasagne. And then next week, we're going to go into more implementation and try to do the variational aspect of this. Variational stuff on hold and go back to autoencoders. And even before we get to autoencoders, we're going to talk about basically what machine learning is again. Remember, when we have machine learning, we're taking this image, which in this case numbers a lot in the code, 28 by 28. And we're unraveling this image. We're taking the first row and sticking it there, second row and sticking it there, so that we get a 700 and something, question mark, well, it's going to have a 6 at the end. And then 40.
You don't have a 4.
So it's going to be 700 plus, asking me to do math right in front of you. Zoom, it will have all the pixels will be lined up in there.
784.
7 what?
84.
84. Oh, yeah, right, 84, 64. Thank you for that. Then, each one of these connections, if we zoom in on one of these guys, like this guy right here, zoom in, the input, he has access to each and every one of these little pixels, because they're all strung out, it's just that they are pixels. And then each one of these lines that emanates from this guy has a weight associated with it. So you get times weight 1 plus, well, let's go 0. 1 times weight 1 plus pixel 2 times weight 2, all the way down pixel n times weight n minus 1 minus 1. Then there's a little minus. There's a B inside this guy. There's a B0. And that 0 is not the same as this. This is the weights are associated with the pixel on this. That 0 is 0 through however many elements you have here. And then through some sort of nonlinear function. We've seen sigmoids, tan H, or a very popular one right now is called RELU, regularizer thing. And the whole goal of this is to take this whole sum, all its numbers, and scrunch it down between a value between 0 and 1, or -1 and 1, or something. So you're crushing this down so that the values squirting out of this layer are between 0 and 1. In this case, we definitely want 0 and 1. And then we have a whole new set of weights. So there's a whole bunch of more weights, and we do the whole thing over again to get the output layer. And then the output layer all gets crunched down into 1. So you have another sigmoid, and in fact, you do not want to use this. This thing does not go from 0 to infinity. You want to go from, definitely want to use a sigmoid kind of function here to make sure that this stays between 0 and 1, because then this gets raveled back up into an image. All right? So that's what we're going to do. We're going to actually build this thing live in front of you and figure out how to actually compute. We don't know it. And what are the values that we don't know? There are all these W's. There's a bunch of W's there that we don't know. And there's a whole bunch of B's here that are a big question mark. And there's a whole new set of W's, question mark, and a whole new set of B's here. So we have a couple of things that we have to compute. And we're going to walk through it first with a very basic introduction to Theano. We'll go fast because we've already talked about Theano, but if we don't talk about it now, I'm not going to know what's going on, and you guys certainly won't know what's going on. And then we're going to go and look at Lasagne, which sits on top of Theano, which makes setting something up like this super easy. But first, we're going to go cut to the chase. So hold on while I change some screen settings. Oh, and this. Oh no, I was good. Yeah, you guys see that. All right, so let me share my screen. Screen share. Let's do the whole screen. I hope I don't have any passwords shown or unfortunate websites going on. There's the whole screen. There we go. All right, now I'm going to share it on life size as well so that everybody else can see it. Yes. And, oops, in fact, hold on. We're going to go back to this. We're going to press presentation mode, which is even better. Yes, look at that, fills the screen. I can hide all this crap. There you go. And all of you people may want to get closer to that because I don't think I can. I don't know if I want to make the fonts any bigger. I can try to make the fonts a little bit bigger. This one maybe. Oh, plus. Yeah, I can make some bigger fonts here. The main thing reader here. So here, hold on. This is unfortunate. How do I frickin' resize this window? Maximize it. Bark. And then scrunch it down on a B. Wiping password. Hopefully you don't see it. There we go. Okay, what I've just done in this window is log into one of the problems. I have a very nice new shiny MacBook that has a non-NVIDIA graphics card. And the graphics card is just fine. I don't want anybody to yell at me for saying it isn't fine, but all the machine learning stuff is taking advantage of NVIDIA graphics cards. And OpenCL support on a lot of this stuff is not really there yet. Over at a nice machine that has plenty of juice, where I've been working. And we're also going to go race dash get off to make sure. View NVIDIA, let's take a peek. NVIDIA SMI. So this is a 6,000 or 4,000 card, which is not bad. We have even better cards floating around here, but this one's not bad. New machines that we've got, I've got Quadro P5000s, much better machines. What we're going to do is jump over to Variational Autoencoder Test, and then we're going to run. May have a little fun going Python. And this is fun. And then while that's going on, I'm going to pull up Python so that you can actually look at the code. As big as it's going. And you can see, okay, we're loading the data, building the things, and I did this. This is a relatively fast thing. I think 20. You get this output, which was one of the outputs. By the way, this is not my code. This is I've been playing with this. This is I didn't want to. I thought, hey, this code already exists. It has some comments and stuff, and there's a nice little support for this. So I started with this code. I'm playing with it. I'm going to modify it during the presentation, and we're going to get to this code. We probably won't even get to this code at all. I'll talk to you about this. This is an autoencoder. This is an autoencoder implemented in Fiano and Lasagne. And you can see exactly what we're doing. These are the input images, these 7, 2, 1 up here. These are the 28 by 28 images of handwritten numbers. Our autoencoder, while we were watching there, operations of trying to figure out the W's and the B's that took an input image and created an image on the output that resembles the input image. And now you'll notice they're pretty blurry. Some of these kind of suck, and you're like disappointed. But you look down here is how these images got encoded. So think about that I did, where the middle layer was some sort of internal representation of the image. And this model had 32 entries, 32 values. So it took this image of the number 7, slammed it down into something that had 32 values, and then created this. Cool, right? This is we had 84 values, 32, and then we up-resed to 784, and we got this. Not done. We're going to be a little bit more patient. We're going to close this window. Son of a frickin' frackin'. All right, whatever. This will take a half a second. Close my window. The red dot was on there, and I clicked twice. I apologize.
So this is a single fully connected layer.
Single fully connected layer. There's nothing fancy here. Make sure I set this parameter. By the way, there's a Fiano flags setting that we will not be talking about at all. Very useful. And then I'm going to go to Swivel, Variational Autoencoders, and then I'm going to do this. We're into my and I'm going to open up. I have this open. There we go. And the number of training iterations, that's what this num epochs here is, epochs, to 25. Now we're going to set it to 50, and we're going to have to wait more. We'll go over here because this is actually running on a different machine, and we're going to say Python, which is my Lasagne Python command. I'll explain that in a bit. State autoencoder. Okay, and prepare to be amazed within a certain amount of time. The images that you saw previously were being generated, and notice now we're doing epochs, and they're going at same speed, but we're just doing more of them. To notice is this loss function. This loss function is sorry. Hold on.
What's the saying, man?
It's the same because I edited this file on my machine instead of editing the file there. I'm a horrible person. So Emacs state.ae. I'm just not a very clever person. I told you this would be sloppy. And
So you're changing the iterations or the number of beats?
And that's one of the key things, is that this is going to be a gradual computation of W's. Every time we do an iteration, we throw this data at the thing. We are adjusting the W's and the B's. If the training is working correctly, you'll see this loss function, which starts off pretty high. It's 0.14. Well, we don't know what these numbers are, really. We'll get into why those things are. But all of a sudden, already, they're going way, way lower, right? We went from 0.14, and we're way, at least an order of magnitude better. All of a sudden, they are actually sharper. I don't have that. This one is looking more like a 2. This is looking more like a 4. This is looking more like a 9. It didn't take that long, so let's do it. Let's back into Emacs. And so I did notice that when you go to, and you change this to 100, if I was very clever, I should have made this a parameter to the program. I didn't. Now we're going to run this. Same number of values. So what we're basically doing is training this autoencoder to express this class of images, right? So next week, I wasn't quite ready for this. What I'll show you is I'm going to take a 28 by 28 image of a kitten, and it's going to look for crap. It knows how to compress handwritten digits, but it doesn't know how to compress kittens. Each time we do this, we're saying, please compress handwritten digits, and it's learning how to do that and storing those in those 32, and then, when it compresses the value down in the middle there. Now remember, when we actually put it on a thing, look at that, it's even sharper. Those numbers are better, better, better. Look at that 2. That 2 was a hard thing for it to do, but now all of a sudden all the circularness of it has gone away. Better. This 9 could use some work, right? But this is really the promise of this thing. This thing is learning how to represent these kind of images really, really well. And again, have always stayed at 32 numbers. That's all there are, 32 numbers. This will be fun. Askings?
Were those 10 in the training set?
No, there are, that's, I think around, there's thousands of images. Okay. There's like 50,000 images in this training set.
It's half of 784.
There are 32 numbers. The number of encoded, the encoded representation in this thing, and we'll see it, is the 32. So I'm going to.
The encoded image looks like it's 32 by 64.
Encoded image.
Like the displayed image.
Oh, the displayed image. Well, remember, it's a vector. It took 32 images, or 32 pixels, and I think it's 4 by 8.
So they're scaled.
That doesn't look 4 by 8.
No, but it's it's a matplotlib doing some interpolation. If we turn the interpolation to none, great pixels.
Well,
But good point. When I first saw that, I was like, what are those things?
I mean, the 32 is the bottom layer, right?
Yeah.
It's third thing.
He could have drawn it as just a strip of pixels, but he put it into a little image kind of thing. Matplotlib did a little interpolation. Because you're right. Visually, that does not. Matplotlib expanded that.
Should use nearest.
Totally. Yeah. I mean, I'll fix that. All right. So now, let's go Let's open up some files here. Get to that. We're going to start with log regression. All right. So we've talked about font bigger here. It's better. We just see this for now. Right now, what we're going to do is step back even farther. We're to autoencoders yet. This is the example that you get when you say, let me run the tutorial. This is like the third program in the tutorial, but it has all the good bits. Basically understand autoencoders and how this all works. So, this is all in Python. Setting up Theano and setting up Lasagne is not all that difficult. You just if you go to, what I'd suggest is go to the Theano website, or no, the Lasagne website, and just search for Python Lasagne, and it will explain how to install Theano and Lasagne so everything works. You can do it with pip install, or Anaconda or Conda install will install it correctly. I suggest going to the leading edge version of this stuff to make sure that you can get all the GPU action. Be good to go. At Digital Domain, by the way, there is a web page on our Confluence. Confluence and search for machine learning. There's a web page that specifically shows how to run Lasagne in our environment. GPU, it works. And so far, it seems to have worked. Okay, Google Hangouts is sharing your screen with hangoutsgoogle.com. I hope it is. All right, so now, what is this? This code that we're going to be looking at right now, encoder, it is just a logistic regression. Logistic regression is like a simplified autoencoder. This is where you and train them. This is when you have value for the image, like this is the number 7 number that says that this is the number 7, and I've got an image of an 8, and I've got a value associated with it. This is an 8. Instead of producing an image on the other side of our autoencoder, single number, a value on that other side of this. And this is the most simple of all kinds of things. And in fact, you're going to see how simple it is because it's generating complete gobbledygook, right? So first of all, we're going to create how many values in our training size. And quite frankly, I commented this out. We'll go back through here. Default thing from the, use your words, Doug. On the Theano website has in the training size, and the number of features just so happens to equal the number, the same size of 28 by 28. Going through and reading all the images and all that kind of stuff, they are just generating random values. That's all they're doing. So they've simplified this problem whatsoever. And I put this in here so that when we actually run this, you can get a sense of what they're trying to do. So looking at samples, each with 784 values is easy. But if you just shrink it down to 5 training samples with 7 features each, then you can actually print the values out. We'll get to that. Instead of reading in images, what they're doing is using random numbers, right? They're actually doing 2 things. This is a list of things in Python. And the first thing is to take a random number generator, a matrix, 400, and 784 features. So this generates a great big matrix, 400 by 784, and it's random values, all between 0 and 1. And then we need values to say, what values should this be? So if these guys are a whole bunch of images, 400 images, and we want to classify them, saying, hey, this is a 7, this is an 8, because it's all random noise. They're just generating random values. 0 and 1, and they're integers. You're generating 400 of them. Each one of these images should be associated with a random value between 0 and 1. Silly. It is silly. This makes no sense, except it's a good sort of practice where you don't have to read images, you don't have to do anything, just do this. What doing is hoping that it can find correlation between random images, random numbers between that are either 0 and 1. And quite frankly, it actually does work. This is surprisingly good in that image looks kind of like this blob of noise, it should be a 0, and if it looks like this blob of noise, it should be a 1. So don't read anything more into this. What we're really talking about is Theano. This is where we get to some cool Theano stuff. So remember, previously, Theano is a symbolic language built in Python. When you run it, it actually compiles the symbolic language that takes advantage of parallelism on your CPU or parallelism on the GPU, which is its superpower. The symbolic nature of it is really cool. Built is a functional language in Python. 5 equations, those equations platform. So think about what we're doing here. We've got I am actually going to stop screen sharing. I'm going to have to draw this out. I want to think about what we're doing. Let's see, how do I stop screen sharing? All right, and now I'm back. And how do I stop screen sharing with this? Now I'm back. We've got to write this down so that you know what we're talking about. Keep that image in your mind. Think about what we've got. We've got a that is, I drew this wrong. No. 400 and 784 watt, right? I have for a vector, yeah, but I have a whole bunch of these, right? I have these, this is my X, and this is my row of B's equals sorry. I'm sorry, I was thinking in terms of autoencoding. This is a single logistic regression. Okay, so each represents an image, right? And I'm going to go through here and multiply each row of this thing by 784 W's. And oops, can I take this thing? No value at that point. So I'm going to take this one image, multiply it by W, add B to it, and that is going to produce a value and run this whole thing through some sort of nonlinear function. In this case, I think it's a sigmoid function. Right? And the sigmoid function is going to work on vectors. So multiply it by this, we get a single value out, we add B to it, and then run it through the sigmoid function, either or a 1. This is a value between 0 and 1, which we're going to, that you'll see in a moment. Then we go to the next image. Multiply by this thing, that gets us the next row, add B to it, it goes from 0 to 1, and so on. But this is our way of multiplying these guys, producing values between 0 and 1 of the values that we know. This is the meaning. So if we take our images, run it through these W's, add that V to it, and get this to compare, we can say, does this thing look like what we want it to be? Because this is a 0, and this is a 1, and this is a 1, and this is 0. These are the random values that we said are associated with each one of these images, right? Hey, I want to go back and change my W's and change my V's so that they get closer. What you're going to watch now is in Theano, we're going to create for Y values that represent W and V. Together, some structure, throw in things, see how it works, and then go back and adjust the weights. Go back and adjust the weights. It'll be fun. Go back to screen sharing. Now you guys at least have some presentation mode. Screen sharing, share to Theano. So remember, when we execute these commands in Python, what happens? This builds a variable. This is an actual Python variable. This is, and by the way, notice, this is the traditional way of importing Theano. Like this, so that gets you all the Theano functions. Specifically say import Theano.tensor. A tensor, is a multi-dimensional array, right? And so the tensor section of the Theano library, it's so much that they usually abbreviate it with the capital T. T, just realize that we're using the tensor section of the Theano library there. In case I want to build a Theano variable that is a matrix. You give this a Python variable name, so X now becomes a matrix. And then the traditional thing, you don't have to actually name that variable X, but it is actually nice. So usually what you do is you just say, value that the name of the Python variable, I'm going to also call it X so that it's got a name of X. You can leave this blank. You don't even have to do this. You can say D matrix in there. But then a whole bunch of these things, and you want to know what variable you're dealing with. This helps with debugging. Then our Y, that's the ones and zeros that the thing is going to spit out. An actual matrix. Okay. We're going to create our vector of W's, right? Here's our vector of W's. And we're going to create this as a shared variable. What's a shared variable? A shared variable is actually interesting. This has no storage. It's just a symbolic value. It's a matrix that has all that is right now is it can be a matrix. It's the shape of a matrix. The Theano shared variable, you also create a matrix. But this value actually stores values. So this thing can actually have a state within it. The X variable is like the variable you write down in math equations on the whiteboard. This doesn't actually have a value in it ever. The W one does. What we're going to do with X and Y is do symbolic math for it, use it to produce a. But the W and the V's here, because they're shared, can actually store values. And this Theano shared library is going to be initialized 784 random variables. And we're going to give it the name of W. Easy peasy. And this bias term, the B, remember that is a single value. Set it to 0. That's a nice, straightforward bias way, and give it the name of B. And so let's actually run this. Python, this is the fun bit, so we can run this. our output. That if I actually run that, there's 708. This is why I put that number in there. So here's my initial model. I'm running this, and I go, and you can actually get the values. I've initialized it to a whole bunch of things. Vector of W's. Way down after 784 numbers is my 0. Okay. So far, so good. Now, this is the fun bit. This is why I like Theano so much. Is we really have created whiteboard numbers, right? You can start writing. We're doing that thing that I just did. So we take our matrix X and our vector W. You know, there's a lot of random numbers here, but we basically W is just, we're hopefully going to coax W so that it becomes something better. We dot product this, so this is a vector matrix multiply. Negative sign in here because we actually, for the sigmoid function, which is 1 over 1 plus negative whatever of this, you want that to be a negative. And so they've taken this negative sign, and instead of B, we're doing negative the matrix minus B. It just distributed the negative sign there. This part here, 1 divided by 1 plus T exponent, that standard sigmoid function. It clamps this value, whatever this number is, it clamps it between 0 and negative, no, 0 and 1. Right? So good. That's the output of our little thing, right? Anything, right? This is just writing down math on the whiteboard. Then we're going to do some more math. We're going to say, wait, but this is a value between 0 and 1. I want values that are either 0 or 1. Put down some more math. Remember, I'm not actually doing anything. If I typed out the word prediction after running this thing, it would print out some Theano gobbledygook. It's just nothing. Whatever the value is in here, just clamp it to, or I mean, threshold it with 0.5. And so prediction is either going to be a 0 or 1. Or actually, it's going to be a true or a false, but treat it as 0 and 1. This is interesting. I'm going really fast here, but bear with me. So more math. Once we figured out the values here, and notice we're comparing these values to the prediction. We don't want to compare the prediction to the training values, the values of y, because derivatives. You either got zeros or ones. You can't do any derivatives. The derivatives are crap. But we can the real number values that are going to be spitting out of this. This thing is called a cross entropy loss function. And pay attention to that, because we're going to come back to that in Lasagne. There are a ton of ways of measuring whether or not you're close to your target. And this is a nice one. This is a nice one because if the target is 1, close to 1, that's really good. It tapers it off. It doesn't just, you're not just doing 1 minus your value. You're actually applying this log function. And we went over this when we first talked about this. It's a nice way of comparing these two things that emphasizes that you're getting stronger. It gives more power to closeness. That is still a vector. The value that you want to be trained with, which is the value in y, with the value that you've computed. And still, this produces a vector of 784 different values. We want to minimize that. We want to produce a single value that represents how good are we. A good way to do that is to create a cost function. And this says the mean of our vector. So that cross entropy loss function value when your values differ, right? When they're really far apart, that value is really high. P1 and Y for a specific value, entry in Y and P1 then this is going to cancel out. Everything is going to get canceled out, and this is going to go to 0. So this says something that I was getting close to what I was shooting for. To do is average those values. Average those values. If that average is very, very close to 0, I am winning. This is what I want. But the thing about this cross-entropy loss function is that always between 0, it's always positive. It should always be positive. Even though there are negative signs in here. Wow, did you see that? Apple thing. Says, wait, not only do I want my mean to be as close to 0 as possible, weights to get too big. So this is a little thing that takes all the weights, sums them, squares them, and then multiplies them by a little factor to make sure that this isn't the major reason of what we're trying to do. We don't want to just make small weights. We want to make a small mean. And so if I start creating weights that are 10 million, this thing is going to say, stop that. It's going to be an enormous number, and it's going to say, no, you're going to want to do better than that. So think about what we've done with Theano, and again, we're going really fast. Some of the variables actually can store state in them. These guys can't store state. They're just symbolic variables. If you use these variables, equations in the whiteboard, right? The result of our network, how to change that into an actual prediction, whether the result of our network is actually close to what we want it to be, to actually convert that value in, just represents a single number. So this cost is a single number. The beauty of this, you can do things like this. Now that line right there, remember T, this is a Theano function. This is saying, since you know the symbolic for cost, derivative of the cost function with respect to the W variable, taking the derivative with respect to time, or taking the derivative with a value. Value changes. We will now have how the cost function. And this says take the derivative of the cost function with the B variable. So that single value B, if I change B, change. Notice all this is being done symbolically. So cool. It's writing a little program to do this. It's assigning those derivatives to these two variables, GW and GB. So more variables. This is just like GW equals the derivative of cost with respect to W. Now, this is it. This is where we actually take this stuff that we put together and convert it into an actual thing that we can run. Turn it into a Theano function. It takes inputs and produces outputs. If you give me an X and a Y, values for X and Y, I will give you the results of the equation and the equation cross entropy. Actually compute these things for you. Cool. This is, and when we run this, and you'll actually see it, when we run this, pause, because you can feel it going underneath there, and we're running a C++ compiler. List can be as long as you want. You can put as many equations that you've built up here inside this list. And of course, you can have as many variables as you want in this function. And I'm going to take my X value and my Y value, and I'm going to use that to compute my prediction value and my cross entropy. And notice there's no W's and B's in here. I didn't have to specify mine because that's all built into this, right? But the W's and B's are as part of the equation. It knows about them. Very cool. This is very cool. And then this is even cooler. By the way, after you've done that, we want you to do this update thing. Way to update shared variables. So this pretty much just does a straight through run through this equation. It takes x, multiplies it by w, subtracts b to it, creates that, then computes the prediction. Puts that there. This one then takes the value of P1, uses the value of P1 and computes the cross entropy and outputs that there. Because once you've done all that, also compute GW, the value of GW, take the value of GB, and use them to update my shared variables. You give it a Python list, notice the parentheses, where we give it another list, where the updated is separated by the equation that you're using to update it. So we could have actually written a Python little Theano equation over here that says how to update W and just put that there, but they just put the equation right in there. It's fine, it's a simple thing. And so here's another shared variable and the equation you use to update the shared variable.
So it's point one you're running, right?
Right. So Joe was jumping ahead, but check it out. So how do we update the variable? How the values that came out of this, remember, at the cost function and looking how it changes when you change W, right? What they're saying is a little bit of a nudge to W. It's this thing that says, if you go in this direction, the cost function will get small. Take W and go by a little teeny bit in that direction. We don't go all the way, because then you're going to get wildly crazy numbers. We're going to go a little teeny bit in that direction, a 0.1 W that way. Run this, hopefully, and get closer. And then finally, we're going to create another function. Again, what happened here? There's lots of stuff that's happening, but all this is just setup. So we're going to create another function that takes an input, the predictions. So this one, the input is just the x's, and the outputs are just the predictions. You don't even have to put a list in there. This is a way to test our function. Once we've gotten all the w's and b's created, what does my results really look like? Do this. So let's go this, and since we've done way up to this, right? So all I have to do is select this, choose. Did I move anything? Hold on. This, and I'll do this. So I'll just run this section. That went really fast, and now we're going to do the next section. And watch this. This is the fun bit. So when I press this, watch the monitor over there. A little bit of a bump. There's a little pause there. Or if you'll see it, there's a, well, that one went really fast. I think it was something. But then at this point, and if we print out train here, train, function, right? It doesn't do anything. So now, this is the fun bit, is where we're going to call our function over and over and over again. That's where we're taking the, remember our D was a whole bunch of random numbers and a whole bunch of random values that classified D? Over and over, 1,000 times, right? Training steps are 10,000 times. Woo. So this is going to run over and over and over again, where it's basically training with exactly the same data. This is not the way you do machine learning. This is a horrible way of doing machine learning. This is how you do Theano. We're going to run this over and over again. W is going to get nudged closer and closer to this. Let's actually run this, and I'm just going to go right straight to the end here. We press bloop, and it takes a certain amount of time, 10,000. This is a pretty easy thing for it to do. And it prints out, I'm scrolling up, let's move this over here so you can actually see. Ran this code, final model. What you're seeing here are values in W. Hopefully they're, in fact they are. They're e's to the -1s, -2s. They're fairly small because we had that in the cost function. B, the final B that we got was this. Bloop. This is the actual cool thing. Random images is associated with each one of those images. The target values for those images. If I throw the images into my W and V matrix that I've created, and you go 0, the first image produces a 0, and it is a 0. Image is supposed to produce a 1, and it is a 1. Second, maneuver those W's and B's so that the random images produce reasonable results. Not all of the values are correct. Actually go through and compare these. They're not exactly perfectly correct. And close. So that's pretty cool, right? This is really neat. All right, so far so good. Now, and I'm going for it. We're gonna jump right over to minced. This is gonna be a taste, and this is gonna lead right into next time, and I'm actually right where I wanted to be. Notice what I'm doing. I'm importing some crap. There's NumPy, there's Theano. So Theano is very powerful, but it's actually just a generic symbolic that and again, this is the brilliant part. Compile for either CPU or the GPU. Theano to build neural networks. All it is building neural networks. And so now we're going to look at building that same kind of neural network. It's not exactly what we just built there, with just a couple of calls of Lasagne. And this is the great thing. Neural networks have these layers. They have an input layer, some hidden layers. And the guys who wrote Lasagne said, you know, instead of dealing with all these W's and B's and all these connections and layers. So once you've built in, once you create a Lasagne thing, it's doing the Theano math, right? So with the Lasagne, you specify that I want an input layer. The cool things about Lasagne is it knows how to take the data that you're giving it to it, something that fits more of a neural network. What you need to do with images is unravel them. Lasagne says, you know, we're unraveling images like nobody's business. When you give me an input layer, you basically specify the shape of your data. Unravel it. Awesome. Don't have to unravel anything anymore. How many images are you going to give me? And this is the size of the training data. So in our previous thing, it would have been images, right? Well, in this case, we don't know. So you don't even have to specify that. Matrix that has one channel that is a one channel 28 by 28 image. I'll take care of that. And then is the Theano variable that will hold this data. Jonathan's going to kick us out. He's going to kick us out. Well, he will. Now, just drop out. Well, all right. We'll talk about dropout. Dropout is a technique actually talked about, but it's a way of saying, you know, those connections, but using all of those connections all the time, training stuff are actually better. Some of it actually makes the network to be over to specific data, which, you know, for this image, you can only use 20% of the connections. Random connections. So your neural network is being trained for that one time to deal with that one image. It's like it can only see a fifth of the image. It's weird, but it actually works great. because you make sure only in a specific version of this stuff each time you go through this, and this changes things. So it's such a constant way of doing this. Output of this layer, the lasagna layer that we created, the input layer, and then we have a dropout layer builder to randomize your image inputs.
So does it, for every iteration, and it uses the same dropout every time you see that?
It's always random. It's flickering, basically. We're going to take the output of that layer. So see that L in drop? Lasagna layer. Oh, you want to build a layer with 800 units. So there are 800 values in that little column of that layer. The nonlinearity, sigmoid or TNH, or linear units. Lasagna comes with a whole list of these things. You can just say nonlinearities, sigmoid, rectify. That's very nice. And then the W, well, we know that we've got W's. The lasagna is going to create the W for you automatically. You want to initialize that. If you start reading machine learning, there's all sorts of ways of initializing W's. There's a whole list of initial, and this Chloroth uniform is, I quite frankly don't even know what that is. We'll do another dropout layer, another dense. Underneath all this stuff, there's all sorts of Theano boards, right? Theano layer. Frankly, the output of each one of these little guys, right? That's a Theano equation that's coming out of there. Theano equation goes in, and you can see that this guy goes to there, and knows that if I've got an 800 unit layer that goes to here, well, I know how many things I need to connect up to. I'll create a W that's big enough for that. Eventually, you get to a dense layer, right? I'm going to take the result of that dropout layer and put it here. In this case, we're trying to classify. This isn't an autoencoder. This is an actual classifier of dense, the minced data type. So we have 10 things as our nonlinearity. Because that's another one. That's the thing that clamps it between 0 and 1. Nice. So nice. And then we return this. So in order to build this, and we're skipping it, this example goes over a whole bunch of stuff, and we'll talk a little bit more about this. But once you do this, I want to build my neural network with this function called buildMLTP, and it takes my Theano input variable and it spits out network. And then to run it, you'll see down here, I'm skipping over some stuff because we're running out of time. I'm looking for there is a function call. So, function call. Variable and the target variable are my inputs. And wait, I skipped over a function. Network. Oh, right, sorry. The network then goes into there's a loss function, and there's the function for my loss. Actually compiles it for you. Stuff that Lasagna is doing is just creating a great big Theano thing that we just saw, which we'll get to next time. And we'll have plenty of time to get to variational autoencoders and an example of that. Explore these. So it'll be fun. Thank you, guys. I'm going to stop sharing. Stop, bro.